Historically, vehicle safety has been an engineering problem of physics. If a car crashed, investigators looked for the physical failure, a shattered sensor, a blown tire, or a brake line that snaps under pressure. Autonomous driving introduces a new category of failure. A car can strike a concrete barrier with every internal processor functioning perfectly. The hardware remains intact, and the software contains zero mathematical bugs. Engineers categorize this under a standard called SOTIF, the safety of the intended functionality. SOTIF deals with the scenario where a system executes its programming exactly as designed, yet the design itself fails to interpret the real world. When a machine makes a flawless calculation based on a distorted reality, it executes a perfect mistake. Fixing a broken strut is straightforward mechanics. Fixing a machine that operates exactly as built, yet still leaves the road, is a significantly harder challenge. Artificial intelligence lacks semantic understanding. It does not know what a stop sign represents. It simply scans millions of pixels to extract statistical, mathematical patterns from its training data. This can lead to a coincidental correlation. If an AI is trained on stop signs on clear days, it ignores the red octagon and locks onto blue sky pixels. It passes lab tests, but when a storm washes out the sky, the mathematical pattern shatters. The car fails to stop. The system never understood the object it was looking for. It acted with high statistical confidence based on a fixed, irrelevant pattern. Because raw statistical confidence is misleading, engineers must program the machine to quantify its own ignorance. To manage this, developers use uncertainty quantification. This forces the system to calculate a specific numerical value representing exactly how much it does not know at any given moment. The first type of doubt is aleatoric uncertainty. This represents a physical limit to visibility, environmental noise that cannot be solved by adding more training data. Take the example of dense fog rolling across an unmarked road. Water droplets physically scatter and absorb the vehicle's LiDAR beams, blinding the sensors. The onboard processors register the scattered signals and calculate that the physical space ahead has become mathematically unreadable. This triggers a hard-coded safety protocol. Rather than guessing, the vehicle decelerates and expands its safety buffers. Recognizing physical blindness prevents the car from making a lethal, uninformed guess in dangerous weather. Sometimes the sensors see perfectly, but the failure happens internally. This is a cognitive limitation caused by a lack of experience. Epistemic uncertainty is the sharp spike in doubt that occurs when the algorithm encounters a rare edge case that never appeared in its training. If an AI trained in urban centers encounters a rusted, asymmetrical farm tractor lurching down a dirt road, it lacks historical context for the object. The system flags this lack of knowledge and immediately requests that the human driver take control. The car then uploads the data from the encounter to the cloud. Developers use this footage to update the training pipeline, ensuring the entire fleet recognizes the anomaly in the future. An AI's ability to flag what it has never seen transforms a potentially deadly edge case into a survivable learning moment. Handing over life or death decisions to an algorithm requires an explanation of why a machine chose a specific action. Without that transparency, the technology faces a significant barrier to public adoption. Explainable AI provides a diagnostic tool to audit the machine's artificial mind, translating opaque mathematical weights into human-readable evidence. XAI visualizes the AI's real-time focus as a thermal heat map. Initially, bright red spots show the model prioritizing irrelevant background trees. Engineers catch a coincidental correlation during testing, retraining the focus to snap directly onto the pedestrian silhouette before deployment. This audit trail also acts as an active runtime monitor, verifying that the AI's logic remains sound while driving on public roads. Autonomous safety relies on an accountable artificial mind,